Some materials, like metals, are able to conduct electricity, but electricity is nothing else than the movement of electrons, and electrons can be generated or used up during a chemical reaction. We are very familiar with this concept since we use batteries every day. A battery is nothing else than a device used to store electric energy as chemical energy. The movement of electrons in chemistry is a characteristic of redox reactions, where electrons are moved between different species. In this redox reaction, when metallic zinc comes in contact with a solution containing copper ions, copper 2+, electrons are transferred from the metallic zinc to the copper ions, resulting in the formation of zinc ions, zinc 2+, that will go in solution, and solid copper, copper 0, that will deposit on the metallic zinc. This reaction can be divided in an oxidation reaction for zinc and a reduction reaction for copper. If we could divide these two half reactions in two separate containers, between them there will be only exchange of electrons, or electricity. This is exactly what happens in a galvanic cell, the most basic example of a battery. A piece of zinc is immersed in a solution of zinc ions, and a piece of copper is immersed in a copper solution. These solutions are called electrolytic and are also able to conduce charges. In both electrolytic solutions, the counterion is sulfate. We have just defined two electrodes. The pieces of zinc and copper are then connected with a wire. Since they are connected, electrons will start flowing from zinc to copper. Metallic zinc will go in solution as zinc 2+, and ions of copper 2+ in solution will deposit as solid copper on the copper piece. Since electrons move from zinc to copper, zinc will be called the anode, and copper will be called the cathode. Now we have a problem. We are moving electrons, which means that we are moving charge. This means that the electrolyte solution of the anode will be enriched in cations, since zinc 2+ is created, and the electrolyte solution of the cathode in anions, since copper 2+ is consumed. To balance the charges in the solution, a salt bridge is used to connect them, where the anion and cation of a chosen salt will flow to the right electrolytic solution to counterbalance the created charge imbalance. This is the structure of a galvanic cell, and most batteries follow a similar structure. Pay attention to one thing. Electric current, by definition, flows in the opposite direction of electrons, since it follows positive charges. If instead of generating electricity, we are using it, we have an electrolytic cell. In this case, we are using electricity to cause a non-spontaneous chemical reaction. Electrolytic cells are used for electroplating, the process of covering a metal with a very thin layer of another metal. This is used, for example, in the production of jewelry. Note that the name for cathode and anode are switched, since the anode is always the electrode from where electrons flow out. But how can we know if a spontaneous redox reaction will happen between two electrodes? We use the standard cell potential, a measure of a potential difference between the electrodes of a cell. This is the difference of the standard reduction potential energy of the anode and of the cathode. In our galvanic cell, the cathode will attract electrons with a potential of 0.34 volts, and the anode will generate and lose them with a potential of 0.76. The difference, 0.34 minus 0.76, 1.1 volt, is the standard potential of a cell. To obtain that potential for an anode or cathode, the standard hydrogen electrode, or SHE, is used as a reference electrode. For example, if we have a copper electrode and a standard hydrogen electrode, the standard potential of a cell is 0.34 volts. 0 from the standard hydrogen electrode and 0.34 volts from the copper. In this way, we can define the half reactions potentials. Since the potential is positive, it means that the copper electrode is the cathode and the standard hydrogen electrode is the anode. The standard reduction potential energy for a half cell will also help us define if the electrode is the positive or negative electrode. The positive electrode is always the one with the highest standard reduction half cell potential. In most cases, this potential is positive, while it is negative for the negative electrode. The use of a standard electrode allows us to define a series of potentials for different metals and lets us visualize in an easy way what would be the result of a combination of any given redox couple.